All right, so you have that in the chat. So now let's tackle this first question. It says in the following drawing, the green spheres represent atoms of a certain element. Oh, hold on 1 second. 1 second. Sorry about that. So it says in the following drawing, the green spheres represent atoms of a certain element. And then it also says the purple spheres represent atoms of another element. So that means that there's a reaction about to take place. When you see this written like this on the left side of the arrow, even though we haven't done this yet, this is always your reactants on the left side. And on the right side of your arrow, products. All right, so anytime two atoms or elements come together and they react, this is a chemical change. All right, so now let's look at what it says. The purple spheres represent atoms of another element. If the spheres of different elements touch, they are part of a single unit of a compound, right? So that's over here. So both of these are compounds made up of two atoms of different elements. It says the following chemical change represented by these spheres may violate, this is the key to the question right here, may violate one of the ideas of Dalton's atomic theory, and it asks which one. So can somebody look in the chat, look at those 5 principles, and somebody tell me what number 5 says? Actually, it's in this particular case, it's number 2.
Are you talking about the atoms are indivisible and indestructible?
And indivisible and indestructible. Good. Now look at the reaction and tell me what happened on the right side. What's different on the right?
Is it because the green material doubled?
Yes. So you actually have 2 green atoms over here. How many did we start with?
1.
Only 1. So what does that mean? What is that? What did we do going from reactants to products?
It divided.
It either divided or we created something new, right? And in a chemical change, new atoms don't get created. They just rearrange. So can you divide an atom?
No.
No. The rule just says that it's indivisible and indestructible. So you can't divide it and chop it in half. So this actually violates this principle. I'm just going to say the principle of indivisibility. Let me see. I'm going to run out of room. Does that make sense? Anybody not catching that? Right. You can't make new atoms up. If they're not there at the beginning, they don't just magically materialize on the other side of the arrow. Right. So you can't divide atoms. You can't make new atoms. And so based on that information, we have to say that it violates that rule of indivisibility, where you can't divide atoms in half or destroy them or create them, right? They're either there or they're not. All right. Let's look at any questions about that. All right, let's look at the second question. And it's a question dealing with the law of constant proportions. And it says, if 19 grams of oxygen are in a sample of aluminum oxide, we haven't done nomenclature yet, but Al2O is the chemical formula for aluminum oxide. Let me ask this question for somebody who has who can remember this. Let me see. Let me see if you've been paying attention. What if? How would I write that? How would if I pull that apart using like the crisscross method? What would the charge on aluminum be? Anybody?
I feel like I think it's a plus charge on it because I
Okay,
know the
it's a
oxygen.
metal. Yeah, it's a metal, so it's gonna have a plus charge. I agree with that. But what is the numerical value of the charge? You in the ballpark. So remember we said with the crisscross method, right? The subscript, if you look at the subscript, then you can kind of tell which charge went where, right? Because you crisscross like this. So this number is going to come here like that. And this number is going to come here like that. So if you pull them apart, then the subscript is going to go back to here. And then the same thing with this one. This will go back to here. That's just a aside. We're going to talk a lot about that between Friday and coming Wednesday. But yeah, I just wanted to see if anybody caught that. All right. So this is again a problem dealing with constant proportions, and it asks how many grams of aluminum are in the sample. What's the strategy here? What's the first thing we need to do if it's a problem dealing with the law of constant proportions? Right.
We
Whenever
have to find out the total weight, right, of the aluminum oxide.
okay, let's think about it. Do we need the total weight or do we need the atomic masses of aluminum
Atomic masses, I
and
meant, my
oxygen?
bad.
Yeah, you good, you good, you good. So we need aluminum. Can't write with a highlighter, Russell. We need aluminum and oxygen, right? Because the law of constant proportions says that for a sample of a given compound, the ratio of the atoms in that compound is going to stay constant no matter where the sample comes from. All right, so we got aluminum and oxygen. Can somebody look up aluminum's not molecular weight, atomic mass? Right, if you don't have a periodic table, you can. My suggestion is just download one from the App Store or the Play Store because you're gonna need that for
27.
27. So that's 27 AMU for aluminum. And then what about oxygen?
16
Okay,
16.
16
AMU.
AMU oxygen. All right. So for aluminum, and oxygen, we can say that 27 grams of aluminum is going to be 16 grams of oxygen. But now remember, we're working with Al2O3, so we got to take these subscripts into account. So in this compound, there are 2 aluminum atoms, 3 oxygen atoms. So we're going to take that 27 and multiply it by 2, I'm sorry, 2. And then we're going to take the 16 and multiply by 3. And that's because of these subscripts right here. Right, so that's that 2 is for here. And then for oxygen, we'll stick that right there. You got to take all of that into account. All right, so when we do that, we can say that 54 grams of aluminum equals 48 grams of oxygen. So now we have our ratio, right? This is the ratio that we'll use to interconvert between aluminum and oxygen for any sample of aluminum oxide, all right? No matter where that sample comes from. So let's do that here. Let me put a box over here so we can work this out. How am I going to set that up? Because this is basically a conversion factor. So I'm asked up here about grams of aluminum, and I have grams of oxygen. How am I going to set up the conversion factor? What number am I going to put on top?
You'll put aluminum on top and then oxygen on the bottom.
Okay, good. So 54 grams of aluminum over 48 grams oxygen times 19 grams of oxygen. So the grams of oxygen is going to cancel. Let me fix that 48. It looks like 4 degrees. All right. Somebody help me out with that calculation. Punch that in real quick.
$21.38 AMU or grams of aluminum.
To 21.38.
Yes, sir.
All right, we'll leave it in 2 sig figs. So we'll just say 21 grams of aluminum. Anybody not see that or have a question about it? So when you're dealing with constant proportions, the first step in the strategy for solving that is to get the atomic masses. And then you make sure the mass numbers match by ensuring that you take whatever subscripts are there and include them by multiplying the atomic mass by that number. So that's why we multiply the atomic mass of aluminum, which is 27, by 2, and the atomic mass of oxygen, which is 16, by 3, right? So we can get a full accounting of the mass of that compound. All right. Any questions? All right, let's go to the next question then. We only got 2 more questions left to do. The last one, I'm gonna break y'all out and have you work on it for a few minutes and then come back and we'll discuss it. It's actually a really good question. All right, so it says, so this is a question dealing with the law of multiple proportions. That particular law is number, let me see in the chat. Number 5. Atoms of different elements combine in fixed whole number ratios when forming compounds, right? So you can form multiple compounds from certain atoms, and they're going to combine in fixed whole number ratios, right? So in order to solve a multiple proportions problem like this one, right, we're going to have to get a fixed mass of one of our atoms. That's what it's going to require. Let's zoom in. Right. And then after that, you're going to compare. This is the second part of the strategy. Right. You're going to compare the masses of the second atom. So you get a fixed mass of 1. So whenever we say that, we just say that it's 1 gram. We're going to reduce one of them to 1 gram. And then we're going to compare the masses to see if they give us a small whole number ratio. All right. So let's read the question. Somebody read the question.
Two different compounds are formed by the elements carbon and oxygen. The first compound contains 42.9% by mass carbon and 57.1% by mass oxygen. The second compound contains 27.1% 62.3% by mass carbon and 72.7% by mass oxygen show that the data are consistent with the law of multiple proportions.
Okay, good, good, good. So I'm highlighting in different colors what they gave us, and then this is what they're asking us. All right, they're asking us to show that the data that are given line up with the law of multiple proportions, which says that if for a fixed mass of any compound, any atom in a compound, the mass of the second atom, when you compare it to the mass of the second atom in whatever different compound is formed by those same two elements, you should get a small whole number ratio, right? So here it gives us these numbers. So we're going to say for compound 1, we're going to assume 100 grams of that compound. That way we can just take those percentages and turn them into grams. So we'll assume 100 grams. That means that the compound 1 is 42.9 grams of carbon, and we set that equal to 57.1 grams of oxygen. All right. Now we want to get that fixed mass. So the fixed mass, we're going to stick with carbon. Let's use carbon for our fixed mass. Right. So this is going to be 40. We're going to divide both sides by 42.9. Can somebody run that calculation real quick? That's going to be 1 gram of carbon equals what? Anybody?
1.33.
1.3, excellent. 3 grams oxygen. All right, let's do the same calculation for compound 2. And we're going to assume 100 grams of that as well. All right, so we got, what are our numbers? 27.3 grams equals of carbon equals 72.7 grams oxygen. So let's make carbon our fixed mass. What do we have? Should be 2 point something.
2.66.
2.66, good. All right, so now that's the first part. We got our fixed mass, we made it carbon. So now what we want to do is take the masses of oxygen and put them in a ratio to see if we get a small whole number ratio. All right, so that's going to be right. So we'll take the masses of oxygen, and we're going to just put 2.66 here, put 1.33 here. And what do we get from that? Isn't that a 2-to-1 ratio? Right, if I divide 2.66 by 1.33, I should get 2 to 1. Is that right? So this is it matches. It follows the law of multiple proportions, because the ratio of the masses of oxygen in this compound reduces to a small whole number ratio. Somebody asked this morning, what happens if you get a big number, like if the numbers in the ratio are large. If that's the case, then you can always reduce it. If those numbers are divisible, you can reduce it that way, or you can divide both numbers by something that they're divisible with, and that should give you a smaller number. All right. Any questions about that problem? All right, let's go to the next problem. All right, so we've looked at constant proportions, the key to those problems is to take the atomic mass and find the ratio between the atomic masses, and that ratio is constant for every sample. And then multiple proportions, where we take the compound itself and the masses of each atom in the compound and take one of those masses and make it 1 gram. And then the other mass of the second atom, we find that based on that 1 gram. And when we compare the masses of the second atom, we look for a ratio. That's a small whole number. All right, let's go to the next one. I want to break y'all out into breakout rooms to work on this. Let me see, we got 20 people. I'm gonna do 4 rooms. And that way, where's my breakout button? There we go. I'm gonna do 4 rooms, 5 people per room. All right, so what I want you to do, I want rooms, when I open the rooms 1 and 2, I want y'all to attack this as a constant proportion problem to find out if these numbers follow the law of constant proportions. And then rooms 3 and 4, I want y'all to attack it like a multiple proportions problem to see if the numbers follow multiple proportions. Let's see what we come up with. So I'm open this up, open these rooms up, and everybody should join the room you're assigned to. I'll give you 10 minutes to work on it. I think 10 minutes will be plenty of time. All right, so find your breakout room and join it. And then and after 10 minutes, we're gonna come back to the main room. All right, we got a couple of people haven't joined yet. Go ahead and click that little breakout room invitation so you can jump in. Got 1 person left. All right.